Now an ideal gas not only satisfies the equation of the state, that is PV is equal to RT, but its specific heats are constant also. Now for real gases, these vary appreciably with temperature and a little bit with the pressure. Okay. Now the properties of a substance are related by this equation, that is TdS is equal to du plus P into dV. Right. So if you divide everything with temperature, you get ds is equal to du upon T plus P upon T into dV. Now if you talk about U, that is the internal energy. Now internal energy is assumed to be a function of temperature and volume. That is, U is a function of temperature and volume. Okay, so this means that du will be equal to the partial differential of U with respect to T, keeping volume constant, into dt, plus the partial differential of U with respect to V, keeping temperature constant, into dV. Alright, so this is a very important relation. Now when you look at this equation and you substitute the value of du in the above equation, okay, so you get the value of ds is equal to 1 upon T into du. That is this complete equation, and this would become curly U upon curly T, keeping volume constant, into dt, plus curly U upon curly V, keeping temperature constant, into dV, plus P upon T into dV. Alright, now let's manipulate it a bit further and multiply 1 by T inside the bracket. So you will get 1 by T into curly U upon curly T, volume constant, into dt, plus 1 by T into curly U upon curly V at constant temperature, into dV, plus P upon T into dV. Alright, so if I look at these two terms, this term and this term, I have dV upon T and dV upon T as a common value. So I can rewrite this as ds is equal to, you will have 1 by T into curly U upon curly T into V into dt, plus I can take 1 by T to be common, into, so I can write it down as curly U upon curly V at constant temperature, isn't it? And dV would then go outside, plus P into dV. So this is the equation that we get after putting in the value for internal energy as a function of temperature and volume. Also, the value of specific entropy is a function of T and V. So I can also say that S is also a function of temperature and volume. So similarly, I can find out ds, which would be equal to curly S upon curly T at constant volume into dt, plus curly S by curly V at constant temperature into dV. Alright. Now let us denote this equation as equation 1 and this equation as equation 2. So let's put these equation against each other. So you will get curly S by curly T in at constant volume into dt, plus curly S upon curly V at constant temperature into dV is equal to 1 upon T into curly U upon curly T at constant volume into dt, plus 1 upon T into curly u upon curly v at constant temperature plus P into dV. So this is what you get. Now from this equation, okay, or from this complete equation, let's compare these things, and I can say that this is equal to this, and this is equal to this. Okay, so when you compare these two equations, you can write down that curly S upon curly T at constant volume into dt is equal to 1 upon T into curly U upon curly T at constant volume into dt. So we are basically comparing the constant value to constant volume terms and the constant temperature terms. Alright, so from this I can strike off dt and dt. So this would give me that curly S upon curly T at constant volume is equal to 1 upon T into curly U upon curly T at constant volume. So this is a comparative equation that we get after comparing equation 1 and equation 2. Let's go on to the next term. Let's equate this and this. So from here you can strike off dV from both the terms, and we get the equation as curly S upon curly V at constant temperature. Okay, this is equal to 1 upon T into curly U upon curly V at constant temperature plus pressure. So this is the second comparative equation that we get. Okay, so let's name these equations. Let us name this equation as equation 3 and this equation as equation 4. So now let's differentiate equation 3 with respect to V again at constant temperature. Okay, so let's bring this equation down. So what I'm going to do is I'm going to differentiate equation 3 with respect to small v at constant temperature. Okay, so when you do that, so it will become a second order partial differential. So you'll get curly square S upon curly T into curly V. Alright, this is equal to 1 upon T into curly square U upon curly T into curly V. So this is what you get. Okay, and let us name this or number this equation as equation number 5. Now let's differentiate equation 4 with respect to T at constant volume. So it's the opposite of what we did for equation number 3. So now what we are doing, we are differentiating equation number 4 with respect to temperature at constant value of volume. Okay, so this equation we are going to differentiate, and the equation would then become curly square S upon curly T into curly V. Okay, this is equal to, so these are two functions. Basically the first function is 1 by T. Okay, so this becomes minus 1 by T square. Okay, and the other would be the differential of this particular function. So let's multiply it first. So if you multiply it, you get 1 upon T into curly U upon curly V at constant temperature plus P upon T. So this is what you get. Okay, let's differentiate this first. So when you differentiate this, let's put the first function as it is and differentiate the second one. You will get curly square U upon curly T into curly V. Okay, so this is what you get. Right, now let's differentiate this function. So this would become minus 1 by T square, and this part would be as it is, curly U upon curly V at constant temperature. Alright, now let's come to this part. So let's keep 1 by T as it is, plus 1 by T, okay, into curly P upon curly T at constant volume, and then I will have to differentiate 1 by T. So it will become minus P upon T squared. Okay, so let us say this is equation number 6. So this is quite a complex, you can say, differentiation calculation, but not very difficult. Just a little bit of concentration is required to stay on track. Okay, now let's compare equation number 5 and equation number 6. So when you compare these two values, you can equate. So you have the value for this and this. So you can equate this part equal to this part. Alright, so when you compare them, you have the values as 1 upon T into curly square U upon curly T into curly V is equal to 1 upon T into curly square U upon curly T into curly V minus 1 upon T square into curly U upon curly V at constant temperature. Okay, so this is what you have. Now if you move ahead a bit, this would be equal to plus 1 by T into curly P by curly T at constant volume minus P upon T square is the last term that you would have. Alright. Now from this equation I can strike off these two terms directly. Okay, and let me take these two terms on the left hand side of the equal to sign. So you'll have 1 by T square into curly U upon curly V at constant temperature plus the pressure. This is equal to 1 upon T into curly P upon curly T at constant volume. Alright, now I can do one thing. I can strike off this T and this square value, and this equation will then reduce to curly U upon curly V at constant temperature plus P is equal to, this T would now go up on the other side of the equal to sign, and then you'll have curly P upon curly T at constant volume. So this is the result that we get after the comparison of these equations. Now if you talk about an ideal gas, okay, now for an ideal gas we have this equation, PV is equal to R into T. Now let's differentiate it at constant volume with with respect to temperature. So you would have V into curly P upon curly T at constant volume is equal to R. Alright, so if you again look at this, you can say that curly P upon curly T at constant volume is equal to R upon specific volume. So we are talking about this particular term over here. Alright, and from this particular equation, that is the equation of state, so R upon V can be written as P upon T. Okay, so let us say this is equation number 7. Okay, now let's compare. So let first of all give it a number 8 and this as equation number 7. Okay, so now let's put the value of curly P upon curly T at constant volume, which is equal to P upon T, in equation number 7. So let's see what magic this does. So you'll get curly U upon curly V into T plus P is equal to T into P upon T. Okay, so T and T can be cancelled, then P and P can be cancelled. So ultimately what you get is you get curly U upon curly V at constant temperature is equal to 0. Let's say this is equation 9, and let's put this into a good looking yellow box. Alright, so this is you can say a very important thing that you get. Now therefore from this equation, that is equation number 9, I can say that U, that is the specific internal energy, it does not change when V changes at constant temperature. Similarly, if I say that U is a function of temperature and pressure, it can be shown that curly U upon curly P at constant temperature would again be 0. This means that U would not change with P when the T remains constant. Okay, so U does not change until the temperature changes. So whenever the temperature is constant, U will never change even if your volume and pressure are changing. So this gives us a very, very important relation that we all always say that U is a function of temperature. So this is quantifying that relation, that U is only a function of temperature. So whenever T changes, okay, unless T changes, U will not change. And for an ideal gas, this particular equation, that is U is equal to F of T, this is known as the Joule's law. So I hope you understood this video in which we explained that how internal energy is only a function of temperature in the case of a ideal gas. Now let's take this discussion a bit forward in the next